So here's a question for you. Not sure exactly why you would want to do this, but let's pretend for a second that you are doing this. You're flying in an airplane, and that airplane is traveling at 800 kilometers per hour. And you throw a baseball inside that airplane. I wouldn't recommend this, not only because of safety reasons, you might break something, but it would probably get you in a little bit of trouble if you threw a baseball in an airplane in midair. But let's say that for whatever reason you do that. It's traveling at 800 kilometers per hour. You throw a baseball at 100 kilometers per hour. What's the relative velocity of the baseball? In other words, what's the velocity of the baseball relative to the ground? Relative to the airplane, it's 100, right? But relative to the ground, it isn't 100. If you're standing on the ground and this airplane is made out of glass, which is even more reason not to throw a baseball if it's made out of glass. Okay, but let's say it's made out of glass so you can see inside it. How fast is the airplane? Sorry, how fast is the baseball moving relative to you on the ground? It could be 900 kilometers per hour, or it could be 700 kilometers per hour, depending upon which direction you threw it, right? If you threw it either towards the front of the airplane or the back of the airplane, the velocity of the baseball relative to the airplane in either case will be 100 kilometers per hour. But relative to the ground, it would either be 900 kilometers per hour or it would be 700 kilometers per hour, depending upon which way you threw it. If you're trying to find the velocity of that baseball relative to the ground, in effect what we're doing is adding vectors together. We have an airplane that has a velocity of 800 kilometers per hour. We have a baseball that has a velocity of 100 or 100, depending upon which way we throw it. If we add those two vectors together, we will get the relative velocity of the baseball, how fast the baseball is moving relative to the ground. Make sense? Adding vectors together, we learned to do that in grade 6, maybe just not in the context of a problem like this. Intuitively, though, we knew this already, right? Intuitively. You're in an airplane, you throw the baseball, it's going to be moving faster or slower than the airplane is moving, right? Hey, just a quick little question here. Does anybody know the only thing that does not obey that rule? There's one thing that doesn't obey that rule. If you throw it at a certain speed in something that's moving, you can't add the vectors together to get the relative velocity of it. It's light. Yeah? The speed of light is always 3 times 10 to the 8 meters per second, 1 billion kilometers per hour, relative to no matter what. It's kind of wacky. If I'm in my car traveling at 500 million kilometers per hour, which is pretty hard to do in your car, right? And you turn your headlights on that travel 1 billion kilometers per hour, the velocity of the headlights relative to you is 1 billion, but relative to the ground, it's also 1 billion, which has all kinds of crazy implications like things getting shorter, things getting heavier, and time slowing down. Leads to all kinds of crazy things. But that's the only thing that does that. Everything else behaves like this. Okay, everything else behaves like adding vectors together. Okay, vector addition. 800 plus 100 is either 900 or 700, depending upon which direction you're adding them in. So of course, to get the relative velocity, really all we're doing, as we said, is adding vectors together. What if you don't throw the baseball in the direction the airplane is moving or opposite to the direction the airplane is moving, but what if you throw it across the airplane? So across the aisle. In other words, perpendicular to the way the airplane is moving, or even at some funny angle relative to the way the airplane is moving. How would we find the relative velocity now, the velocity relative to the ground? Or we're still going to add vectors together. To find a relative velocity, we add vectors together. But if we throw it perpendicular to the way the airplane is moving, we're not going to add them according to the grade 6 rules of vector addition. We're going to add them according to the grade 11 rules of vector addition, the rules that we learned here over the last week. In other words, If I throw a ball at 100 kilometers per hour to the east, the airplane is moving at 800 kilometers per hour to the south, then I would add those two vectors together just like this, and the velocity relative to the ground, or the relative velocity, would be the resultant vector, the sum of both of those vectors. And we know how to find that, right? We know how to find that red line vector. We do the Pythagorean theorem, and we can find the angle by using the inverse tan function. When I'm doing these problems, I like to separate my vectors into two categories of vectors. I call them, and this is just my name for them, so you're not going to see this in a book anywhere. I call them solid line vectors and dotted line vectors. The solid line vectors are going to be the vectors that contribute to what actually happens to the object. The dotted line vector is what actually happens. Now, why don't I just call them blue and red? Well, maybe you don't have blue and red. We have to, especially in these questions, have a way of distinguishing between those two types of vectors. For me, I can draw them always blue and red, or green and red, or whatever the case may be. For you, maybe you only have one pencil, and you've got to distinguish in some other way. So I'm suggesting that you distinguish between them as solid line vectors and dotted line vectors. That resultant vector will be my dotted line vector. And the resultant vector is a result of the other vectors. So in other words, where does the baseball actually go? Where does it really go? Dotted. Where the baseball goes, the dotted line vector is a result of where I throw it, a solid line vector, and the motion of the airplane, another solid line vector. Solid line vectors contribute to where something goes. The dotted line vector is where it actually goes. Make sense? Solid line vectors contribute. Dotted line vectors, or resultant vectors, are the result of the solid line vectors, the result of the things that contribute. Now, I'm going to here's some examples of solid line vectors, things that contribute to where something goes. Let's say I'm a pilot of a plane and I aim to the north. Now, I don't end up going to the north because there's a wind, but that's where I have my controls pointed, is to the north. I'm aiming to the north. Well, that's not where I actually end up going, but it contributes to where I go. Let's say that I'm the captain of a ship and I'm heading directly west across a river, but there's a river current taking me to the south. Well, I don't actually go to the west, but I'm aiming, or I'm heading to the west. So that contributes to where I actually go. Where do I actually go? I'm not sure. But I know that that's going to contribute to where I go. Clearly, where I aim or where I head is going to play a part in where I go, right, Gunther? How many people drive here? How many people have their driver's license? You ever driving down the highway and the wind is really, really strong coming from the west, like a Chinook wind or something, and like it's really strong, like 60, 70, 80 kilometers per hour, which happens sometimes. And it's like you're fighting to keep the car on the road. Like if you don't pay attention for 2 seconds, then you're going to blow right off the road. You ever notice sometimes that your steering wheel is turned way over like this so that you can drive straight? You ever notice that? It's like you're aiming somewhere over there northwest so that you can end up going straight north. Where you're aiming contributes to where you go. It's not where you go because you're going north, but you're aiming northwest to fight that wind. It contributes to where you go. We call that a solid line vector. The airspeed, that would be the speed. Typically, we're talking about an airplane here in this case. This would be the speed of the airplane if there wasn't a wind present. In other words, not which direction the airplane aims, but how fast the airplane aims. I don't think WestJet has this, but Air Canada does. Every time I've flown Air Canada, they're going through that safety stuff, The flight attendant is going through that safety stuff. And what I'm doing prior to that, and sometimes even during that, I shouldn't be, but is flipping through that magazine. And at the back of that magazine on Air Canada, they have a list and pictures and statistics about all the flights, all the airplanes that Air Canada flies. Like, so the 767 and the 747 and the Airbus A whatever, and so on. And in all of them, it lists the airspeed of the airplane. 800 kilometers per hour, 900 kilometers per hour. That doesn't mean that's how fast the airplane is actually traveling. That means that's how fast the airplane can travel if there's no wind, no tailwind, or no crosswind, or no headwind. Okay? How fast the airplane can travel when there is no wind. That contributes to how fast the airplane actually goes. It's not how fast the airplane goes, but it contributes to how fast it goes. Yep. I'm sorry? I don't know. I don't know how they measure that. The wind speed or the river current also contribute to where I go. You ever tried swimming across a river and with a current in it? Well, if you aim directly across the river, you don't end up going directly across the river because the river current, in addition to where you aim, right? Where you aim contributes to where you go, but so does the current contribute to where you go. Maybe you're flying. If you're flying a glider or an airplane and you want to go directly north to Edmonton, but there's a wind going to the east. We have to aim in a different direction because the wind contributes to where you actually end up going. Where you aim does, but so does the wind contribute to where you actually go. These are all solid line vectors, things that contribute to where you go. Versus dotted line vectors, which don't contribute to where you go, it's where you actually go. They result from solid lines. Where I actually go, where I'm aiming directly east across the river, there's a river current to the south, I end up going to the southeast. Okay, the solid line would be where I aim, and the river current, the dotted line would be to the southeast where I actually end up going. Or where I want to go. If I want to go directly north, then I don't head directly north. I head northwest to account for the wind. Where I want to go could be considered to be a dotted line vector as well, the result of my two solid line vectors. And finally, a dotted line vector would be, just like in that first example we gave you in one dimension, the velocity relative to the ground. How fast is the baseball moving relative to the ground? Well, that's a dotted line vector because it's a result of how fast the airplane is moving and how fast I throw the baseball. The ground velocity, or the velocity relative to the ground. You can imagine how if you were a pilot or the captain of a ship, how this might be somewhat relevant to be able to figure out where you need to aim or head in order to end up in a specific place. Okay, you need to be able to do vector addition. You need to know which vector is which. Okay, which one we make as a solid line vector, which one we make as a dotted line vector. Okay, here's an example. Keep in mind as we're doing this example, really all we're doing is vector addition, okay, which is what we've been doing over the last several days. We just have to keep straight what's our solid and what's our dotted line vectors now. So it says the pilot of a plane heads directly north to Edmonton at a velocity of 200 kilometers per hour. However, there's a wind of 50 kilometers per hour blowing to the east. And this is a big deal. If you're in an airplane that can only travel at 200 kilometers per hour, and there's a wind that's 50 kilometers per hour to the east, I would think, I'm not a pilot, but I would think that would be a challenging flight. Where does the plane actually go? You got to figure that so what do we do here? Well, we've got really three vectors here where I'm aiming or heading and which way the wind is going and then which way I actually go. Something is to the north at 200. Is that a solid or a dotted line vector? That's a solid because that contributes to where we go, right? where I aim or where I head contributes to where I go. It's not necessarily where I go, but it contributes to it. So I'm going to draw a solid line vector to the north, 200 kilometers per hour. Notice that the vector is no longer a displacement vector, it's a velocity vector. Listen, I can add any vector I want as long as I'm adding the same quantity. So if you're adding displacement, that's fine. Add displacements. If you're adding velocity, that's fine. Add velocities. Make sure they're all velocities. So 200 kilometers per hour to the north. Then I got a wind blowing to the east. Does that contribute to where I go, or do I end up going directly to the east? That contributes, right? So I'm going to draw that as a solid line vector as well. Now, just like over the last number of days, we're adding two vectors together, two solid line vectors together. We got to draw them front to back. So I got a couple of options here. I can draw this right here. Or where else could I draw it? Where else could I draw it? Position 1, 2, or 3. 1, 2, 3. I could have also drawn it in position 2, right? Because that would be drawn front to back, right? I can't draw in both places. One or the other. Both cases, though, I'm left with my vector diagram drawn front to back. Now, my resultant vector, or my dotted line vector, where the plane actually goes, is going to go from start to finish. So the captain of this plane ends up going somewhere northeast. Don't know exactly where. Let's find the value. R is going to be the square root of 200 squared plus 50 squared. We do exactly the same thing, except it's with kilometers per hour instead of meters. And theta is going to be the inverse tan function of opposite over adjacent, 50 over 200. Again, it doesn't matter whether it's displacements or velocities, we do it the same way. This is 206.15 kilometers per hour. Now round it to two significant digits, we'd make that 2.1 times 10 to the 2 kilometers per hour. What's my angle? 14 degrees. And what would we say there? Alex, 14 degrees, what of what? Not north of east. Where are we measuring it from? Are we measuring it from the north, south, east, or west? We're measuring it from the north. So we're going to say it's not north of east, it's rather it's east of north. Now, if you had drawn it the other way, it would have been 76 degrees north of east in that case, right? So where do I end up going? 14 degrees east of north at more than 200 kilometers per hour. Does that make sense that maybe I could actually travel more than 200 kilometers per hour? Yeah, the wind's helping me. Not helping me as much as it could if it was a tailwind, but it's still helping me. Make sense? Okay, let's do another example, and then I'll set you free to work on some questions here, okay? Okay, let's take a look at this next one here. This one says the captain of a ship aims her ship east at 20 kilometers per hour, but there's a current of 10 kilometers per hour, puts the ship off course. Where does the ship actually go? This current, by the way, should be to the north. Doesn't say that, but it should be to the north. Puts the ship off course. Where does it actually go? What do I got here? Aims her ship east at 20 kilometers per hour. Is that solid or not? Why is that solid? Because that contributes to where she goes. Where she aims isn't where she goes. Where she aims contributes to where she goes. We'll make that a solid line vector. There's a river current in the water that's 10 kilometers per hour to the north. Is that a solid or dotted line vector? That's solid. Why? That's a current, and a current contributes to where she goes. So we're going to make that a solid line vector. I'm going to draw it up here. There is one more place, but I could have drawn it, though. I could have drawn it down here, because that would have made it front to back as well. Doesn't really matter, but of course, don't draw it in both places. Now, my resultant vector, which I'm going to make my dotted line vector, It's drawn from start to finish, and that's where she actually ends up going as a result of all this. Let's find the value of r, and let's find the value of theta. R is 20 squared plus 10 squared, square root. I think that's 22 kilometers per hour. And theta is equal to the inverse tan function of 10 over 20, 27 degrees. What would we say there? 27 degrees what of what? East of north? No. North of east, because I'm measuring it from the east. So north from east, north of east. Had you drawn it the other way, you could have got east of north, but it would have been 63 degrees east of north, which would have been equally correct. I would like you now, right now, to take a look at your worksheet. This is the last worksheet in your booklet. And I want you to do questions number 1 to 4 for now.